This is Raju. In this video, I am going to explain about the topic Quicksort. Quicksort was developed by Charles Anthony Richard Hoare in the year 1962. Quicksort works as follows. In Quicksort, first we need to select an element called pivot in an array. We divide the array into the two parts such that all the elements in the first part are less than or equal to the pivot, and all the elements in the second part are greater than the pivot. Less than the pivot are placed towards the left side of the array, and greater than the pivot are placed towards the right side of the array. After doing this, we need to recursively apply the quicksort algorithm to the first part and then to the second part, to the left part, after that, and to the right part. Coming to the quicksort algorithm, the quicksort algorithm uses the idea of divide and conquer. Divide and conquer means we need to first divide the array and apply the quicksort algorithm. As I said you in the first slide, we need to select an element called pivot which divides the array into the two halves in such a way that all the elements in the left are smaller than pivot and the elements in the right half are greater than pivot. The elements less than pivot are placed left side and greater than pivot are placed towards the right side of the array. Here also same thing. For writing an quicksort algorithm, we need to follow these three steps. First, find pivot, divide the array into two halves, and quicksort the left half part and the quicksort the right half part. Same as I said in the first two slides. You can see the partition algorithm. I have written the algorithm using the lower boundaries and the upper boundaries. Array of lower boundary is taken as a pivot here, and this is also a partition algorithm. To that first slide, you can see swap. I have used here swap. Here in this is a algorithm for quicksort. This is a main algorithm. By using this algorithm only, we are going to solve the next example. Okay, let's getting into the example. Here I have considered an array of elements having 7, 6, 10, 5, 9, 2, 1, 15, 7. You can see here I have taken in the box here. Here 0, 1, 2, 3 are the array index, and 7, 6, 10 are the array elements. The main rule should follow is elements less than pivot be left side of pivot, elements greater than pivot be right side of the pivot. By using this rule only, we need to solve the algorithm. Here I have chosen 7 as pivot and the start is 7. Is start is less than or equal to pivot? Yes, 7 is equal to 7. So we need to, if the condition is yes true, we need to increment the start. Increment takes place. So the start is now in the index 1. You can see in the down box, you can see that start is in the index 1. Here again start is 6 and pivot is 7. Is start less than pivot? Yes, start is less than pivot. So again increment takes place. The start is now moves to second index, that is number 10. Here after incrementing, the start is at 10 and the pivot is as usual 7. Is start less than pivot? No, start is 10. 10 is not less than 7. Okay, the condition is false. No, when the condition is false, we stop incrementing the start and we start moving the left end, and we start moving the left to the side, left side. We found greater element than pivot here, so we need to stop incrementing start. Now if you found the element greater than pivot, then we need to decrement the end. Here I have written left, it is end point. We need to decrement the end now. Now here the end point is 7 and pivot is 7. Is n greater than pivot? No, the condition is false. So we need to swap the left start and the end. Okay, when the condition is false, that is when the end condition is false, we need to swap the start and the end. Here after swapping, the 7 comes to the second index and 10 goes to the 8th index. You can see in the down box here. Again in the down box, the start is at 7 and pivot is 7. Is pivot less than or equal to, is start less than or equal to pivot? Yes. The condition is yes. So we need to increment the start. The start is next moved to the index 3. Here the start is 5 and the pivot is 7. After swapping, the 5 is taken as start and 10 is taken as end. Here is start less than pivot? Yes, start is 5 and pivot is 7. Yes, 5 is less than 7. The condition is true. So we need to increment the start. Now start moves to the index 4, that is towards 9. Here in the down box you can see that the start is 9 and pivot is 7. Is pivot less than, is start less than pivot? No. Start is 9 and pivot is 7. So we need to stop the increment and we need to move the end towards the left. Now going to the end point. Here the end point is 10 and pivot is 7. The condition, apply the condition. Is end greater than pivot? Yes, end is 10 and pivot is 7. So we need to decrement, move the end point towards the left, that is to the index 7. After moving, the end point is 15 and the pivot is 7. Here is end point greater than 7? Yes. Again we need to move the end point to the index 6. Okay. Since 15 is greater than pivot, we need to move the end point towards left. Here again the end point is 1 and pivot is 7. Apply the condition. Is end greater than pivot? End is 1 and pivot is 7. No, it is false. So we need to swap the start and end. Then we need to swap right and start and end. After swapping the arrays, you can see the array after swapping down here. 1 goes to the index 4 and 9 comes to the index 6. Here again we need to take the start. Start is equals to 1 and pivot is equals to 7. Apply the condition. Is start less than pivot? Yes, start is 1 less than 7. So we need to increment this start. Start is next moved to the index 5. Again here down, start is taken as 2 and pivot is taken as 7. Is 2 less than 7? Yes, we need to increment the start. Here the start is 9 and pivot is 7. Is start less than pivot? No. 9 is not less than 7. So now here start stops moving and end starts moving left. End is 9, pivot is 7. So end greater than pivot? Yes, 9 greater than pivot. So we need to decrement the end and now end is moved to the index 5. Here you can see that end point is less than starting point. Here end is 2 and pivot is 7. Here we need to swap this end point and the start point, but we are not going to swap these two because they are already start already start as crossed the endpoint, so we should not swap end and start. And now here we are going to swap the end element and the pivot element. Here end element is 2 and pivot element is 7. We need to swap these two elements so that 2 will come in the 0 index and 7 will come in the 5th index. You can see here 2 is in the 0 index and 7 is in the 5th index. Here the pivot has settled in the index 5 and the left subarray is all less than 7 and right subarray is all greater than 7. Now you can check all the elements less than pivot or left side and all the elements greater than pivot or right side. Apply the same rules to the left subarray and to the right subarray. After that we get the sorted array. This is a quicksort algorithm. Now let's check the sorted array. Here you can see the sorted array 1, 2, 5, 6, 7, 7, 9, 10, 15. This is called the quicksort algorithm. Let's coming into the time complexity of quicksort algorithm. Time complexity of an algorithm signifies the total time required by the program to run till its completion. It is the total time taken by the program to complete the run. Here the time complexity of an algorithm is most commonly expressed using the zero notation, O notation. It's an asymptotic notation to represent the time complexity. We all know that the time complexity is the total time required to run the program till its completion. Okay. Next, here time complexity of a quicksort algorithm. In the worst case, for each element, partition position is to be happen in the edge of the array that results in skew tree of height n, and hence the total complexity becomes 0 of n square. Here again in the in the best case, for each element, partition position happens to be in the middle that results in a balanced binary tree of height log n, and hence the total complexity is 0 of n log n. In the average case, it is same 0 as n log n. We need to remember that when the elements are already sorted in the ascending order and descending order, the complexity is this. If they are not sorted, we need to sort and apply the time complexity. Okay. Thank you guys for watching my video. I hope you all understand the concept that I have given now. Thank you.